All right, so get this. Microsoft says they've built a quantum computer chip that uses a new state of matter.
Wow.
Yeah, I know.
Yeah.
It sounds like Star Trek, right?
It does.
But this is the Majorana 1 chip,
Right.
and it's based on something called topological superconductivity.
Yeah.
Stick with us today.
Okay.
We're going to break this down.
Sounds good.
See if this chip could really revolutionize computing
Okay.
as we know it.
What's really interesting to me is that Microsoft is betting big on this being the key to what we call fault-tolerant quantum computing.
Okay.
And that could change everything.
All right, so before we get ahead of ourselves, let's back up a little bit.
Okay.
What exactly IIS, topological superconductivity?
So think about regular superconductivity for a second.
Okay.
You have electrons pairing up
Okay.
and flowing through material with zero resistance. It's like a perfectly choreographed dance
Okay.
where the dancers just glide effortlessly across the floor.
Right. I vaguely remember that from physics class.
Yeah.
Something about Cooper pairs, right?
Exactly. But here's the thing.
Okay.
Regular superconductivity is kind of delicate. Any disruption in the material can kind of mess it up.
Oh.
Topological superconductivity is different.
Okay.
It's like a fortress protecting those dancing electrons.
Okay.
It's inherently stable.
Yeah.
Because it's based on the overall structure of the material itself.
Interesting.
Not just the local conditions.
So it's like the information is encoded in the very architecture of the material.
You got it.
Wow.
And that's where these mind-boggling particles called Majorana fermions come into play.
Wait, Majorana fermions?
Yeah.
I'm all ears, but that sounds a little intimidating.
They are pretty wild. I'll give you that.
Okay.
Imagine a particle that is both itself, its own antiparticle.
Whoa.
In the quantum world, these particles are kind of like a magician's trick.
Okay.
Appearing and disappearing in a way that completely defies our everyday understanding of reality.
So if I meet a Majorana fermion, should I ask it for an autograph? Since it's both itself and its opposite,
Yeah.
I'd get two for the price of one, right?
But here's why these Majorana fermions are so crucial for quantum computing.
Okay.
They allow us to create topologically protected qubits.
Okay, remind me, qubits are like the bits in a regular computer,
Right.
but they leverage quantum mechanics
Yes.
to be much more powerful.
Precisely.
Yeah.
And the problem with regular qubits is they are incredibly fragile.
Yeah.
Even the tiniest disturbance can throw off the calculation.
Oh.
But by using Majorana fermions, we can create qubits that are inherently shielded from those errors.
Interesting.
That's the beauty of this topological protection.
So are you saying that Microsoft is essentially braiding these mind-bending particles together
Yeah.
to make these super stable qubits?
That's a great way to visualize it.
Okay.
Think of it as a complex dance where the order of the steps, or in this case, the braiding of the Majorana fermions,
Yeah.
actually changes the outcome of the dance.
Wow.
It's this braiding that lets us perform quantum computation
Okay.
in a much more robust way.
So hold on, braiding particles.
Yeah.
That sounds insanely difficult.
It definitely is. But Microsoft seems to have made some serious breakthroughs with the Majorana 1 chip. They've designed it specifically to harness these Majorana fermions.
Okay. Let's say they're right. And they can actually pull this off.
Okay.
What could it mean for quantum computing?
That's a great question.
I always hear about things like faster drug discovery.
Yes.
And breaking encryption.
Right.
Is that the kind of impact we're talking about here?
Those are definitely some of the potential applications.
Okay.
Fewer errors means more efficient and reliable computations. We could see incredible advancements in fields like drug discovery, material science, and even financial modeling.
So let me try to put this into concrete terms for our listeners.
Okay.
Instead of taking years to develop a new drug, could we use a topological quantum computer to, say, simulate the folding of a protein at the atomic level and accelerate that process to a matter of months?
Yeah.
That's exactly the kind of breakthrough we're hoping for.
Wow.
Imagine being able to design drugs tailored specifically to your body's needs with fewer side effects and greater efficacy.
That would be a game changer for medicine.
Absolutely.
And what about material science? What kind of possibilities open up if we can manipulate matter at this level?
We could design entirely new materials with properties we can only dream of today.
Wow.
From super strong but lightweight materials for building skyscrapers to incredibly efficient solar cells for clean energy.
Wow.
We're talking about materials that could revolutionize entire industries.
That's incredible.
Yeah.
Okay, my mind is officially blown. But I have to ask the practical question. How do they actually make this stuff? Is it some kind of special material?
That's where the real magic happens, at the intersection of material science and engineering.
It takes incredibly precise fabrication techniques to create what are called heterostructures. Imagine carefully layering semiconductors and superconductors together with atomic level precision.
So it's not something you just stumble upon in nature?
Not usually.
Okay.
And even then, maintaining the right conditions, like extremely low temperatures and precise magnetic fields, is a massive engineering challenge.
Sounds like we're still in the early days for this technology.
We are.
Yeah.
But even though the Majorana 1 chip is a major step forward, there's still a long way to go.
Yeah.
We need to figure out how to scale up these systems, make them last longer, and develop algorithms that can actually take advantage of this new type of quantum computer.
So it's not like we'll have topological quantum computers on our desks next year?
Probably not.
Okay.
But the progress is incredibly rapid, and the potential is enormous. We may be looking at a future where quantum computing is used to solve some of humanity's biggest problems.
That's what I love about this show. We get to explore these amazing possibilities, even if they're still a ways off.
So what's next for this research, in your opinion? What are the big questions scientists are trying to answer?
One of the big ones is definitively proving that these Majorana fermions really are behaving the way we think they are.
Okay.
Remember how we talked about braiding those particles?
Yeah.
Well, the way they interact follows a special set of rules called non-abelian statistics. It's like a complex mathematical dance that governs how these particles exchange information.
So it's kind of like choreographing a dance at the subatomic level and then proving the steps are following the right pattern.
Exactly. It's incredibly difficult to control and measure these particles.
Yeah.
But there have been some exciting results recently, so it seems like we're on the right track.
That's great to hear. What happens next? Is it just a matter of building bigger and better chips?
It's not quite that simple. Scaling up these systems,
while maintaining the delicate conditions needed for topological superconductivity, is a major engineering hurdle.
Right.
And then there's the software side to think about. We need to develop entirely new algorithms that can leverage the unique capabilities of this type of quantum computer.
It sounds like a truly collaborative effort, requiring advances in materials science.
It is.
Physics engineering, and even computer science.
Absolutely. And that's what makes it so exciting.
Yeah.
This research is pushing the boundaries of so many different fields. Who knows what other discoveries might emerge along the way?
Now that we've got a handle on the mind-bending science, let's zoom out and think about what this means for you, our listener. Why should you care about these tiny particles in this new state of matter?
Because this is the kind of research that could fundamentally change our world. We're talking about the potential to design life-saving drugs, create new materials with unimaginable properties, and solve problems that are currently impossible.
That's a pretty compelling reason to care. But even if those breakthroughs are still down the road, there's something profoundly inspiring about this research, isn't there?
Absolutely. It's a testament to human curiosity.
Yeah.
And our constant pursuit of understanding the universe around us, even at its most fundamental levels. And who knows, maybe in the process we'll discover things that are even more amazing than we could have ever imagined.
Okay, so we've talked about the incredible potential of this technology. But with any powerful new tool, there are always potential risks. What are some of the things we need to be thinking about as this technology develops?
One very real concern is the potential for job displacement. As with any new technology that automates tasks, there's a risk that quantum computers could lead to job losses in certain sectors.
That's a valid concern. What else should we be thinking about?
Another issue is the potential for misuse. Imagine a quantum computer powerful enough to break the encryption that protects our online transactions and national security.
Oh, wow.
That kind of power in the wrong hands could have serious consequences.
So we need to be thinking about safeguards and regulations to make sure this technology is used responsibly.
Absolutely. We need to ensure that the development and deployment of quantum computing is guided by a commitment to responsible innovation. We have to have open and honest conversations about the potential impacts of these technologies and work together to ensure they are used for good.
This has been an amazing conversation, and I'm sure our listeners are just as captivated as I am. But sadly, that brings us to the end of our deep dive today.
As you continue to learn about this fascinating field, I'll leave you with this question to ponder. If we can manipulate the very fabric of matter at this level, what other seemingly impossible things might become possible in the future?
That's a great question to leave our listeners with. Thanks for joining us on this incredible journey, and we'll see you next time for another deep dive into the most fascinating corners of science and technology. Until then, keep exploring and stay curious. So we just touched on some potential downsides of quantum computing, like job displacement and misuse.
Yeah.
It's a bit of a double-edged sword, right?
That's the thing about any powerful new technology. It has the potential for enormous good, but also carries risks that we need to address proactively.
So how to navigate this? Who should be responsible for making sure that this technology is used ethically and for the benefit of society as a whole?
That's a complex question, and there's no simple answer. It's going to require a collaborative effort involving governments, researchers, industry leaders, and the public to develop ethical guidelines and regulations for quantum computing.
Yeah, I imagine there'll be lots of debate about where to draw the line, especially when it comes to things like data privacy and security.
Absolutely. We need to have those tough conversations now, while the technology is still relatively young, to ensure that we develop and deploy quantum computing in a way that benefits humanity.
It's almost like we're writing a new chapter in the story of human progress. And we have the responsibility to make sure it's a chapter we can all be proud of.
I love that analogy. And remember, this isn't just about preventing harm. It's also about making sure that the benefits of quantum computing are distributed fairly, and that everyone has the opportunity to share in its potential.
That's a really important point. We need to make sure this technology doesn't exacerbate existing inequalities, but instead helps to create a more just and equitable world.
Exactly. We need to be mindful of the potential impact on different communities and work to ensure that quantum computing is used to uplift and empower everyone, not just a select few.
Well, folks, it looks like we've reached the end of our deep dive into the extraordinary world of topological superconductivity and the Majorana 1 chip. I hope you're walking away with a sense of wonder at the possibilities, but also a healthy awareness of the challenges that lie ahead.
As we wrap up, I want to leave you with a thought. This research underscores that there's still so much we don't know about the universe, and that even the seemingly impossible can become possible when we push the boundaries of scientific inquiry.
So true. And who knows what other mind-blowing discoveries await us just around the corner. Thanks for joining us, and until next time, keep exploring the endless frontier of knowledge.